So in this lecture, we're going to be talking about standing waves, and this really follows up from the previous lecture of the Helmholtz equation, because we actually, since this is a standing wave, we're not going to worry about time because of the definition of the standing wave. So the time dependence is not something we are concerned with. And so for this reason, we're actually simply going to be using the Helmholtz equation, which, if you recall, is the time-independent form of a wave. It's a sort of the spatial component of the wave. That's what the Helmholtz equation describes. So if you recall from the last lecture, and I have sort of the notes up here, I have my time-independent form of the wave function. I'm going to write little y instead of capital Y as my function here, because why not? And so I have minus k squared times y over y of z. And so here is my standing wave. And you notice that there's actually, so if you want to solve any sort of equation here, and here I'm getting a little bit ahead of myself, is you have to have some sort of boundaries. You have to have some system of some sort. Otherwise, I suppose you can solve this for free space, right? In which case it would be a trivial solution. But in this instance, in order to get a standing wave, we actually need to have fixed boundaries. We need to have fixed boundaries, and in this case, we're going to call our so-called fixed boundaries as two different walls. And we're going to call, this distance z, where this wall here is z equals 0. And this wall here is z equals L. L is sort of the length of the wall. And we anticipate that our waves will take on something of this, some sort of form that looks like this. We have one wave that looks like this. So we can imagine attaching two strings on this wall, right? And then we sort of give this some sort of oscillation, and we see what resonates, so to speak. And we will see that the lowest possible frequency, the lowest possible mode, if you will have a particular wave vector, right, or a particular wavelength, if you will, that corresponds to 2 times the length of this wall, right? So it's going to have like a half a period, right, given this particular wave, because you can't get any lower than this, because the next mode up will have a shape that looks like this, and then the next mode after this would have something that looks like this. I didn't draw that very well, but you get the point. And so taking that into consideration, and really this is something I'm kind of foreshadowing here. For many of you, you may think, well, I don't know if they look like that, maybe they don't. And that's fine, and you can take a mathematical approach and you can say, okay, I know that this is my system, right? We only have z, this is just one dimension along z, and I'm saying two things. I'm saying there's a wall at z equals 0 and a wall at z equals L. And if we want that to be true, then by necessity, since the string cannot possibly have amplitude, it can't have an amplitude at these fixed positions of z equals 0 and z equals L, then the amplitude has to be 0. And so what this essentially means is that y of 0 has to be equal to 0. You can't have an amplitude here, because if your string is attached, it doesn't matter what waveform you have, right? Your string's attached, it's fixed here, so it can't move. So y of 0 has to be equal to 0. Y of L likewise has to be equal to 0. And so to solve this equation, well, a good place to start actually is to take a general form of this eigenequation. And we know what the general forms of these eigenequations are. We know what the general form is, a general solution. So general solution. So when you have a general solution, that's not what's important. What's important is really when you define a system and you want to know what the waveform is you have to find the particular solution. And so we're going to find the particular solution, but first I'm going to write down the general. And we have some constant a, some amplitude factor, times the sine, the oscillatory factor, k of z, so k is our wave vector once again, which is simply 2 pi over our wavelength, plus b times the cosine of kz. So what this essentially says is I can describe really any given wave along, throughout space using, presuming I have one particular wave vector k. I can define any wave at any given wave vector using this expression y of z. But of course, this is general, and so the question really, remains: how can we get a particular solution to this problem here? And the way to do that is simply to apply these boundary conditions. And so, if we apply y is of 0, what do we have? We have a times sine of 0 plus b times cosine of 0. And we said that this has to go to 0, right? This has to be 0. Well, we know that sine of 0 is 0, and cosine of 0 is 1. And so we conclude with this that b is equal to 0, right? And likewise, if we apply the other boundary conditions, y of L, we have y of L is equal to a times the sine of k times L, and we know that this needs to be equal to 0. Now b I got rid of because I know b is 0 now. So now we know b is 0, and so we simply have this term here. And this also has to be equal to 0. Well, I pose a question. When is this equal to 0? What does this argument here, because a is a constant, so what does this argument have to be in order for this entire expression to go to 0? Well, we know that the sine of any n times pi, where n is some integer, is going to be equal to 0. So if n is 0, you have sine of 0, which is 0. If n is 1, then the sine of pi is equal to 0. If n is 2, you get the point. Sine of 2 pi is 0, 3 pi is 0, etc. So you have the sine of n pi. And what this essentially means is that given this constraint here, given this boundary conditions, k times L needs to be equal to n times pi, where n is some integer, some positive integer, because negative is trivial. You have the same story, so it's just some integer. And so what this means is effectively k is equal to n pi over L. And it's often convenient to add this subscript here, n, to sort of denote what this n value is equal to. So if I say like k is 2, for example, I know that this lowercase n over here is equal to 2, and so I can simply factor 2 in there. So it's oftentimes written in this fashion. And so to get the particular solution to this, we effectively get this general solution, bring it down here, and we know that b is 0, so this term goes away, and we know what k is equal to. And so we have this y, and I'm going to write this subscript, and actually just to have some space here, I'm going to write the particular solution down here. We have y of n, and I put this lowercase n here, the subscript n, for the same reason I put the subscript n here, is equal to a sine, and I'm going to put this n here because you'll see that the amplitude can actually, depending on how you ultimately solve for this this a sub n can be different, is equal to n pi, so I'm substituting kn, n pi z over L. And this is the ultimate form. Now, this constant here, this constant can be arbitrary, right? It really can be arbitrary. Oftentimes when we solve for that constant, as you will see in quantum mechanics, we want the whole integral from 0 to L to go to 0, or to go to 1, I'm sorry. But we're going to get into that later. There's no need to worry about this now. But this is essentially the form of this Helmholtz equation. The point is, what is the point here? What is the takeaway? The takeaway is that when I have n equaling 1, 2, 3, dot, dot, dot. And I plot these, and let's just call a of n equal to 1 for now. It's not important for the sake of this description. When I plot these terms, these wave functions, you can see for yourself y of 1 equaling sine of pi z over L. Well, obviously it turns out that when z is equal to L, you have sine of pi, and that sine of pi is equal to 0, so that is satisfied. But most importantly, we see that we have half a wavelength here, right? Because it doesn't take a full revolution. It doesn't go around the unit circle. It just goes from 0 to pi. And if n is equal to 2, well, what is that? Sine of, and n is equal to 2, and so 2 pi z over L, right? And so when z is equal to L, you have these cancel out, and you have sine of 2 pi, right? So that corresponds to a wavelength that looks like this. And 3 pi, once again, I'm going to have this node here. Well, this node for this guy. This isn't a node. I have something that looks like this. And this pattern keeps on increasing for higher and higher values of n. And these values of n, for the case of these standing waves, these actually indicate the mode that we're in. The mode, right? Or you can call this the eigenfunction. Or you can call this the eigenstate, or simply the state. Are you in the first state, the second state, the third state? So this would be like the first state, or first eigenfunction. This would be the second eigenfunction. This would be the third eigenfunction, or the third state, and so on and so forth. These are the particular solutions here. And the eigenvalues of all of these, of this particular equation, of this eigenfunction here, eigenfunction, the eigenvalues would be this k sub n term. These would be the eigenvalues, strictly speaking, would be minus k squared. And so the eigenvalues would, strictly speaking, be minus k squared, which is minus n pi over L squared. Right, so these would be the eigenvalues of this equation. So this is a very important concept to know, and we're going to come back to these in quantum mechanics, because the ideas behind eigenfunctions and eigenvalues are critical. This is the whole essence of the time-independent form of the Schrödinger's equation, is this concept of eigenfunctions and eigenvalues, and we're going to get back to it. And so this concludes the lecture of standing waves. I hope this was clear to you all. And in the next lecture, we're going to be going over a coupled oscillator, where we're going to essentially define a system of two oscillators attached to springs and determine the eigenmodes and eigenvalues of that system.